Welcome to this tutorial about the AR Simple Core, in which we're going to show the different scripts and the package mechanics. So the first thing you have to do is to print a marker that is like this, that is going to be in the documentation of your package. Print it and cut it and put it in front of your camera, and you will be able to hit play in your editor mode, and you will be able to show this cool helicopter in real time, or another game object you want in 3D space, and you will be able to rotate the marker, and the helicopter or the 3D game object will rotate it as well. So this is achieved by two modules. One is the image get optimized here, and the other one is the RR Simple Core. So first of all, image tracking. Image tracking is obtained by different steps. If you go to the image tracking script, you will be able to select different images that are displayed into your canvas. So let's understand the steps we take in the process. First of all, we need a gray image. The gray image is obtained by extracting the information of the red, green, and blue colors of the image. Then you can check the binary image, which is going to give you where the marker is, as you can see here. Then we have the Sobel. The Sobel filter, what it does is obtains by derivation of the image the points in which we have lines. So you can see here where the lines should be. Okay, and with those lines we are obtaining the half transform. So the half transform is what you see here in the background. The half transform relates from, or takes us from, the pixel space to the line and theta space, in which we have the rho and theta parameters, which are which correspond to lines in the image. So what we do is, as you can see here, we have some peaks in which the values of the half transform are important. So we are using now a dilatation and erosion process in which we obtain the points in which we consider that we're going to have those lines, or those important lines, in our model. So finally, what we do is label those objects using different colors, as you can see here, in order to detect them. And the ones that are really small, we are going to erase them from the model, and that's what we do thanks to a threshold that is implemented in the game, that is going to be called the mean label size. So you can check at all time the corner values, which are these here. You have the coordinates for the X and for the Y, and you can also check or improve the solution by adding more angle points or more row divisions in the model. So another thing you can do to understand how the package works is DrawOnImage. DrawOnImage is going to explain you exactly what we're doing. So what we are checking in our model is where the lines collide or intersect. So we have 4 lines that we have obtained thanks to the half transform, that are these 4 lines here, and then we intersect them 2 by 2 in order to obtain those points. Then with the corners it's not enough, because we don't know the orientation. So we need to obtain the mean color, as you can see here, the mean color of these squares that are going to be obtained by creating a unity vector that goes from this point here to the center of the marker, and obtaining the mean color of those points there. That is going to give us if it's red, green, or blue. So that's how things are achieved for the tracking. Well, if I pause this for a second, I will be able to explain how the AR core works. So what we do in the fix update after a certain time, it's to relate the points of the marker into the points of the world coordinates. And to do that, we need an homography 8x8 matrix that goes from one dimension to another dimension. And the resolution of that matrix gives us eight values, which are here, that are also displayed on the canvas in the text mode. So you have 1, 2, 3, 4, 5, 6, 7, and 8 values that are going to correspond to the different rotation and translation vectors that affect our model. And those values are also obtained after that process in, you can see here in, I'm going to check, well, we have the verification process. Here, we have the get translation and get rotation from that matrix we need. Okay? So after that, we update the cube transform position using the translation, and then the cube transform rotation using the object rotation. And then we also apply a scale in function of the distance, as you can see here, of the cube side. So that's how it's obtained. Let's just explain this verification matrix process. So in order to verify the matrix, what we're doing is just checking where the points, these points here, must be after calculating the product of the matrix that we have obtained by the original coordinates. And we do that for the first, the second, the third, and the fourth point, and even the center of the pointer, the pointer center of the marker. So those process will give us these points here again in order to verify that we have properly obtained the matrix. If you want to display the values of the matrix, you can also use a function that will it will write the information of the text in the different texts that are there. And this is all regarding the AR core. Then we have a critical step that is going to be checking the different parameters of our camera. So we have an option that is going to be the focal length and the displacement and even the distortion of our camera. So to do that, I have also added a program that you can download from the documentation here from this Google Drive file. And after unzipping the file, you will have these files here. So open your CMD and go to the folder in which you have extracted that information, and you just have to click the calibration exe. So the calibration exe will open your camera, and you will need to print also a chessboard that I will give to you in the documentation. And by just using your camera like that, you'll be able to calibrate your specific camera for this project. So once you have calibrated your camera, you can see how the marker is not calibrated. It only detects the chessboard. Once you have done that, you can open the out camera data XML, and you will have there the information of your sensor. So in this case, you have this value here and this value here, which are the focal lengths, and then the different the focal lengths are here, this one here and this one here, and then you have the CX, that is this one here, and the CY, that is this one here, but you have to multiply those values approximately by 2. So it's approximately what I have done here, and then I have modified it experimentally. Sometimes you have to do that experimentally in order to make things work exactly how you want them to work. So I have done that in our project, and with those parameters you are able to make your AR core work in this simple example with some little errors. So thanks for watching this tutorial. I hope you enjoy it. I hope you consider downloading this package and using it in your future AR projects.